So hello, everyone. So it's my great pleasure to introduce Josef Urban, who he's been working on using machine learning for formalized mathematics. So many of you have probably heard that machine learning has been making some big strides in that direction. But I should say that Josef is not working on this only during past 5 years or 10 years, but maybe nearly 20 years, if I'm not mistaken. So really he has experience in this field quite extent. And he just last year, just a few months ago, he's completed successfully his ERC grant on this topic, sorry. And so he will tell us more about this and yeah, what else should I say? Oh, yeah, I should mention that he's also worked on big formalization projects. So he participated in the Kepler's conjecture formalization and the Mizar libraries, and I'm sure he will mention this more carefully than I do. So, Josef, it's your floor.
Thanks a lot, Mikuláš, and thanks to João and all the organizers for this opportunity to talk to mathematicians at this great anniversary of the Portuguese Mathematical Society. So the title of the talk is Developments in Artificial Intelligence and Theorem Proving. And as Mikuláš mentioned, I have a long history going like almost 25 years back when I basically decided to, instead of doing mathematics, to use computers to do mathematics, because it was sort of the time when IBM's Deep Blue managed to beat Kasparov, and I was sort of an amateur chess player. And I was thinking, well, if we can do it in chess, what are the obstacles preventing us to do it in mathematics and in science in general? So this is a bit of an overview talk about basically where we are today. So the very high level motivation for this work is what I just said, is to basically try to automate mathematical and scientific thinking. And when you sort of go into this meta mode and try to analyze what it is, and obviously I'm not the first one, like there are people like Poincaré and Turing and even Leibniz who studied this quite a lot, then one thing you realize quite quickly is that a lot of mathematics is not just formal sort of deductive reasoning, but it's a lot of more sort of inductive or abductive reasoning. When you are using analogies, you are detecting patterns in your reasoning, and you are sort of learning from both your successes and failures. And there are all these feedback loops when you are trying to prove something and you initially fail, and then you sort of try to see what is wrong, why does it work on a smaller example and doesn't work in the sort of more general case. And so what I basically decided to do as the sort of first step, which so far has taken only 20 years and it's still not finished, is to look for some sort of approximation of something like we do, like when we are, for example, learning from textbooks and solving some exercises and becoming better and better, proving more and more complicated theorems. So the approximation to the textbooks that I found are large libraries of formal mathematics, of formal theories, definitions, theorems, and proofs. And basically, I'm trying to make the machines prove as many of of these theorems, and some of them are pretty hard, as possible. And that's basically the whole setting where we work. So we sort of typically prove something, learn from it, and prove something more thanks to the learning, and then look at the capability of our learning systems and try to improve them by making them generalize better, etc., etc. So why would you do such a thing apart from the sort of very AI-ish and curiosity-driven motivation today, and why would anybody fund such an effort? So it turns out that automated reasoning and automated theorem proving is actually useful today, and it's useful. It's interestingly useful also for mathematics. So thanks to, for example, the development of computer algebra systems and computers in general, and you as mathematicians probably know this quite a bit, we are creating proofs that are computer assisted. They are big and they are hard to verify. So there are these proofs like the proof of the Kepler conjecture, or the proof of the odd order or Phi-Thompson theorem, that are relatively big. And for example, in the case of Kepler conjecture, mathematicians, the reviewers really struggled to completely make sure that the proof is correct, that the proof is bug-free. So that's one use of like basically automated theorem proving, interactive theorem proving formal verification. The sort of more industrial use is that today companies like, for example, Intel, Amazon, Microsoft are funding projects, or even like DARPA are funding projects to verify various parts of hardware and software. So today we really have, like, for example, verified hardware architectures like floating point arithmetics in processors. We have verified compilers. We have verified operating system microkernels, etc., etc. So people even have companies that verify like trading rules for banks, because this is apparently becoming an issue, or transport systems. And the technologies, like the sort of most expressive formalism, which is typically some first order high order logic set theory type theory, for doing these things is sort of exactly the same technology as the formalism for verifying like these complicated mathematical conjectures or proofs. So the field is sort of going hand in hand, driven both by the sort of fancy mathematical projects and the industrial applications of these technologies. And the big issue with this is that the technology is currently quite hard to use, and it's exactly because it's not very smart. So when a mathematician says something like this is easy, this is trivial, you do it by using X or Y, the systems that we currently have are not yet at that level. So they require the people who want to construct the formal proof to do much more work. And because of that, it's tedious. And for example, only a few mathematicians would sort of do that, rather than sort of flying high in their sort of high temperature mode, where they are producing a lot of conjectures and quickly refuting them, etc. So like the formal proof, the computer verified proof, has really a lot of benefits. Like you can really collaborate with the computer in amazing ways. But currently there is this barrier which sort of prevents it for most mathematicians. And like there are these blue sky AI visions that I sort of alluded to. we or many of us believe that mathematics and hard sciences are sort of the pinnacle of human intelligence. And if somebody claims that they can develop strong AI, good AI, well, then they should be able to do mathematics, at least on the human level. And despite all the AI hype that has been happening in the last, let's say, 5-6 years, the AI systems are actually not very good today at doing math at the level at which mathematicians are doing it. So this is definitely a very very interesting objective. And if we manage at least a bit to automate parts of math and science, well, then like the sky is the limit, right? Like we could do like automated physics, for example, right? Like we could really do automated mathematicians and automated sciences. And like there's been plenty of dreams. So on the slide I have Leibniz and John McCarthy, and you can look at these things if you are interested. What is formal mathematics? So I will not do too much on this because of the limited time. So basically, like it's interesting. Some mathematicians know this. Some mathematicians sort of delegate this stuff to logicians. So thanks to this program of, let's say, Leibniz, and then going to Frege, Russell, Hilbert, and I don't know, Gödel, Turing. What happened in the beginning of the last century is that mathematics was sort of embedded in logic, and that's really, I think, that some mathematicians don't even perceive yet. Like it's sort of a creepy revolution that you may or may not acknowledge, or you may even sort of resist it and be a counter-revolutionary. But to a large extent, like these visions have started to be realized because, by the way, like this sort of symbolistic program led to the rise of computers, like by people like Turing and Church and von Neumann, etc. And they, like in the 50s and 60s, people really took this seriously and started to play with the idea of implementing symbolic logic on computers and like formal mathematics on computers. So they started to create systems like Automath, LCF, Mizar, NQSum, ACL2, HOL, Koch, Isabelle. So these are all systems created by these people like De Bruyn, Milner, Tribuets, etc., which you can use to state formally your axioms and your theorems in a way that the sort of computer parses them, understands them. So it's a bit like a programming language. You also state your inference rule in the same way, and then you write your proofs as sort of sequences of the like inference rules, right? So you then use the computer to check that the proof is really going from your axioms to your conjecture, and that each inference is sort of correct according to your specification. So it sounds like a very simple idea. The issue with that, and the main research topic in let's say the formal mathematics or interactive theorem proving field over the last, I don't know, 60 years, is how to actually make it work for mathematicians. Because as I said, the mathematicians typically work on a much higher level than these detailed atomic inference rules, and you need something in between. And people have been creating, for example, more and more complicated proving procedure, like sometimes called tactics in some of the systems, or that they have been programming complicated algorithms to capture the notion of obviousness, like what is it to be an obvious inference. But still, like despite the years of research, like I said, it's still not doing what you mean quite often. But on the other hand, I would say that thanks to these very big projects that happened recently, like the formal proof of the Kaplan conjecture or of the other theorem, these things are really changing, and more mathematicians are sort of coming to experiment with these tools, and the tools are getting better and better, to some extent also thanks to the sort of AI part, the intelligence that we are trying to put into the systems. Here's a quick example, small example, by my colleague from the Netherlands, Freek Wiedeek, about the irrationality of square root of 2. So he always shows this small proof from Hardy and Wright, which shows, I don't know, in 6 steps by contradiction that the square root of 2 is irrational. And I guess each of you has seen this proof, so I will not go through it here. And this is interesting. This is exactly the same text written formally in a proof system called Mizar, where you have keywords like theorem, proof, assume, consider, thus, contradiction, and this is something that really compiles in the system. So the system will basically manage to read this sort of programming language, and it will tell you that there are no syntactic errors. There are not even any like high-level natural deduction errors. So if you sort of manage to justify each of these steps, then the whole proof is really a proof of the goal that you are proving. And what I sort of omitted from this proof sketch are the exact justifications of the steps, which would be typically by referring to some previous theorem or definition in the library. This is the proof of the same thing in a system called whole white, which is a very different system. Let's call it a tactical system. So in that system, you take the goal and you gradually modify and decompose it using tactics. So for example, the first thing is some simplification tactic using some definitions typically. So what does it mean to be rational, etc., etc. And then you can do some rewriting, some discharging, etc., etc. So this is a very powerful method of interactive theorem proving. The systems like whole white are programmable, and they allow you to sort of build up stronger and stronger targeted automation for your theories. So unlike the previous example where, let's say, there would typically be just one method how to justify everything, let's say some weakish first order automated theorem prover. Here you can, if you are into it, if you need it, you can really, for example, program complicated decision procedures in these systems. I think this is the last example. So that's a system called Isabelle Hall. And it's an interesting combination of the two approaches. So the proof is declarative, or mostly declarative, like in the Mizar example. But it also allows you to use more complicated tactics for discharging your goals. So for example, you can say by auto simp, etc., which is some basically simplification procedure inside Isabelle that you can further tweak by giving it various arguments. A big example of formal mathematics is this FlySpec project, which is the formal proof of the Kepler conjecture. So the Kepler conjecture is a conjecture by Kepler, which was stated in 1611 in Prague by Kepler, about the most compact way of stacking balls of the same size in space. And he claimed that it's this sort of pyramid, but there are also equivalent packings that give you the same density. And the conjecture was open until, I think, 1998, when American mathematician Tom Hales, with his student, proved it using a lot of computation. And as I said, the mathematicians had a hard time to review that proof. So Tom decided to do the proof formally, mostly in the whole light system, also a bit in the Isabelle system. And it took about 20 to 30 person years. And in 2014, the proof was finished. So now, thanks to the formal proof technology, we basically know that the Kepler conjecture is no longer a conjecture, but a theorem. But it's a really big formal project with over 20,000 lemmas in all parts of mathematics, many parts of mathematics. And like here is an example of the statements of the lemmas that you are proving there. So written in the whole light language. So you say, if S is a polyhedron and C is a face of S, then C is also a polyhedron. So you have 20,000 lemmas like this. I'll also tell you a bit about automated theorem provers. So this is like a different part of the automated reasoning field, where people are really trying to design programs that will do all the work for you. So you just state some axioms and a conjecture, and you will hope that the system will find the proof automatically for you. So this is one of the oldest AI fields. Like, it comes from 1950s, from people like Martin Davis, etc. And there are many systems today, like Vampire, eProver, Prover 9, etc., etc. They sort of combine various sort of logically based, but you could say a bit brute force style or complete calculi that sort of guarantee that if there is a proof, you will not omit the proof, that you will somehow not miss the proof. And they use like various procedures, like the best known one is resolution, superposition is a big one, tableau, SMP is sort of a newer thing where things are also combined with targeted decision procedures, etc., etc. And typically people equip these automated theorem provers with some sort of human design heuristics that intelligently prune the search space. But if you, like what I did some let's say 15, 20 years ago, try to use these systems to prove facts like, let's say, this fact in the sort of FlySpec project using some, let's say, 10,000 lemmas, then these systems would sort of quickly explode on you, because they typically were not designed for dealing with huge corpora of, let's say, mathematical knowledge. So what I have been trying to do quite a bit is to basically learn from many proofs that are already available in these sort of formally written textbooks, how to select the right knowledge from the big textbooks, and how to guide the current proof using some sort of generalization of the knowledge that has been already used previously. And obviously that's also combined with some sort of brute force search. So I will show you some examples later. And like there is quite a bit of history also to this, like to combinations of artificial intelligence and theorem proving. So you can go back to Poincaré and Hilbert, and like Hilbert's dream to automate mathematics, and the sort of hard undecidability results by Turing and Church. And then Turing is interesting because he basically, in his later work, argues that machines actually can learn anything that intelligent humans can do. So he sort of contradicts the later naysayers like for example, Penrose, who would say that the Gödel theorem is some sort of barrier for machines to do advanced mathematics. And then later in, like, say, 70s, 80s, there is work by Pat Langley and Doug Lennart on, for example, symbolic systems that invent the Kepler laws, or automated mathematician by Doug Lennart, which sort of produces concepts and conjectures in some sort of symbolic, heuristically guided way. And then in the 90s, people started to combine machine learning with automated theorem provers. So that's mostly work of a group in Munich by Stefan Schulz and Jörg Benzinger and others. And as I said, like my master's thesis is some 25 years ago, but when I was trying to basically learn explainable rules from these big mathematical corpora by a technique called inductive logic programming, which is some sort of explainable generalization process. And I would say that since, let's say, 2000, what we have been gradually doing more and more, and the community has been growing, especially in the last 5 years, is to really use large formal mathematical corpora to sort of develop combined methods that sort of both do the sort of deductive theorem proving and learn some sort of knowledge from these corpora that would in turn sort of guide the deductive systems. So it leads to many of these feedback loops. And for people who have learned about deep learning and AI, I suggest this talk of Ben Goertzel, which is, I think, 8 years in 2018, 3 years ago, where he also explains the sort of variety of the AI methods. So even though deep learning is really cool and it gave us a lot recently, there are really many other AI approaches, and I guess nobody really believes that deep learning is the only thing that will make superhuman AI. Like it seems that basically we will need a spectrum of AI methods and that's what also my research is showing. So a bit about what we are doing in practice, or in more detail. So you can divide things into various levels on which you are using the AI or the sort of machine learning to guide the theorem proving processes. So on the very high level, it's this task when you have a big corpus, big textbook, and you have a new conjecture. And if you give the whole corpus, which may have 20,000, 100,000 lemmas in it, to today's automated theorem prover, then it will basically immediately explode and do very little or almost nothing. So the way how you can very significantly improve the performance of such systems is by pre-selecting the right knowledge from these big corpora, from these big textbooks. So that's called premise selection, and a lot of work has been done on that topic. You can also do basically machine learning for selecting good theorem proving strategies or portfolios of strategies for problems, and that means that you need to characterize the problem somehow, and then you need to do the machine learning on like which problems are solved by which strategies. And you could even combine it with some automated invention of new strategies. For example, if you have some language for defining the programs or the strategies. You can also pre-select hints, which is basically related lemmas for theorem proving, and that's a sort of a specific method which is used today for one of the most mathematical things done with automated theorem provers, which is the research on loops and quasi-groups by Bob Veroff and Michael Kinyon, predominantly using Prover 9. And I'll say about it a bit more later, but that's really a very advanced area where these people can produce very long proofs, like 20,000 to 100,000 inferences long proofs. And they really solve open conjectures. So actually this week, Michael Kinyon and Bob Veroff advanced a breakthrough in solving, well, not completely solving, but a major milestone in the AIM conjecture, in the abelian inner mappings conjecture. And they got it by using this technology. So it's one really exciting and practical use of automated theorem proving, guided by these previously created lemmas. You can go low level, so you can sort of guide every inference steps of the automated theorem provers. You can go mid level, so you can take these interactive theorem provers and guide the application of tactics, which is typically some bigger block, like some bigger algorithm. And then you can do all sorts of other things. So you can invent suitable conjectures, suitable concepts. You can try to explore stronger theories. You can obviously do all these feedback loops between proving and learning. And a very interesting, relatively recent task, we've been doing it for some 6 years now, is auto-formalization. So you can take a piece of LaTeX and try to train something like Google Translate to translate it into formal language that you can then proof check. So that seems, especially today, quite doable. It's not totally impossible. I'll show you some examples. Data sets, well, there's quite a few of these libraries, and I will not go too much into them in this talk. Demos, I have some more time, so I will show you at least some of them. So last year we started to do a big evaluation on the Mizar library. So here's one example when we proved the Pythagoras theorem for inner product spaces. So maybe a bit of context. What we started to do last year is to take the full Mizar library, which is something like 60,000 top-level problems, and we are running the learning proving loop on them. So initially, we have an untrained theorem prover, which can prove, let's say, 15,000 of these problems. Then we train some machine learning guidance on these proofs, and then we plug the machine learning guidance into the automated theorem prover. It's called eProver, and the guiding system is called Enigma. And by doing that, the guided theorem prover is smarter and it gives more proofs. And you can do many iterations of this procedure, giving you more and more proofs. So by, let's say, June 2020, we got something like 38,000 proofs, and the current state is that we have about 74% of the Mizar library proved automatically. So that's quite a nice progress. And as part of doing this, let me try to do this Pythagorean thing. We at some point proved this theorem, which you can see sort of written formally and linked, and it sort of shows you how the proofs are done in the Mizar system. So you have some sort of inner product space and 2 points in it which are orthogonal, and then you basically say that the norm squared of x plus y is the norm of x squared plus the norm of y squared. And the way you prove it is that you sort of assume that x and y are orthogonal. Then from that you conclude that the scalar product is 0 by using the definition of orthogonality. And then you prove all these lemmas, and then you sort of start expanding the various definitions and using various theorems to conclude that it actually holds. And click back. So this proof takes 181 steps of inference steps, basically, of the automated theorem prover, of the e-prover. We needed, well, initially, the prover was given something like 342 axioms, which are selected from the big Mizar library, which is something like 100,000 facts in it. And the search took something like 30 seconds. It generated something like 65,000 facts while doing this. And 4,100 of them were selected by the sort of AI in the theorem prover as the good ones, which will likely lead us to the proof. And as the theorem prover is generating these new and new facts, the trained machine learner, trained on the previous proofs, is for each newly generated fact telling us whether this fact is likely to contribute to the proof or not. And we are sort of ranking the facts according to their usefulness and doing the inferences with the sort of most likely facts. So in the end, this leads us to this proof, which consists of these 181 facts that were actually needed. Like these are the steps in the proof. And these steps come from 34 axioms. So if you are really interested, you can click on the e-prover proof, which looks horribly. It's something like this, but it ends with a proof, basically. So that's sort of one sort of concrete example of what we are doing. I could show you a bit more, but I'm a bit out of time, so maybe I'll just show you the last one, which is a bit different on a bit different topic. So this is the auto-formalization demo, and it basically shows you how we try to turn something reasonably informally written, like in the ideal, this would be a LaTeX, how we try to use some sort of trained machine learning parser to turn it into formal expressions, in this case, in the whole light language. And what we are doing on top of this sort of probabilistic parsing is that we are, as we are doing the parsing, we are type checking the formal expressions that are coming out of the parser. And we are trying also to prove them or disprove them by the sort of automated theorem proving systems that are trained over the full flyspec corpus. So we cannot do too much, like the theorem provers are not terribly strong yet. But sometimes this can really work in the sense that we manage to prove or disprove a particular parse of the coming out of the basically system that translates the informal to the formal statement. Well, what also happens quite often is that the system can create an unintended formal parse that is actually provable. So then you can sort of use this system for some sort of conjecturing when you take, let's say, a formal statement, then you informalize it by forgetting about the formal parts of the expression, and then you formalize it back, and that gives you sort of many disambiguations that sometimes can, for example, be more general than what you intended. So this way, we, for example, formalized a statement stated for square matrices to rectangular matrices, and it turned out that we could prove it automatically, and the fact actually wasn't in the whole light library or the flyspec library. So that way you can sort of augment your corpus, your textbook. Let me say a bit about this premise selection. So that's this task of choosing many from a really big corpus, only a few relevant premises, and I'll go a bit fast now. And this is really used today for assisting the users of the interactive theorem prover. So it results in a system called hammers, and it's especially popularized in Isabelle in a system called sledgehammer. And what you can see down here are the success rates of these systems. So these systems take a conjecture written in the language of some interactive theorem prover, translate it to automated theorem proving, let's say, formalism, apply the premise selection. So they choose a small number of the most relevant facts from the big corpus. And if then the automated theorem prover gets the proof, they sort of translate the proof back into the interactive theorem proving formalism. And these systems have become really very useful. So some 5 years ago, we could do like 40 to 45% of the several big corpora. These days on Mizar, we can do something like 60% fully automatically. So it really shows you how much the sort of machine learning methods help. Like the main difference between these 40 and the 60% is basically putting machine learning into the automated theorem provers and the premise selection systems. I'll show you, this is one example of a proof, a complicated long proof like this face of polyhedron being a polyhedron written in whole light. And what the methods can do is that they quite often find an alternative proof. So the trained machine learner sees the 20,000 proofs in this big library, and quite often it sort of sees wider than the mathematician who is formalizing the proof by some sort of standard procedure. And it can see lemmas that the mathematician didn't realize are already there, and that sort of give him much shorter proof, basically. So this is one example where the long proof written by the mathematician has been reduced to an alternative proof, which is much shorter. I think I might skip the internal guidance. So basically, the internal guidance can be done for various automated theorem provers. Like one thing that we did early was to take a simple prover called connection prover or tableau prover called linkup. And it sort of does the proofs in this sort of tableau way where you are closing each branch by having opposite literals on it. And what you can do is basically something like the AlphaGo, AlphaZero for chess playing. So you guide the application of the rules to this sort of proof construction by some learning from the previous proofs, like which rules were applied to which partial proof. And this is actually leading to a quite good improvement. So if you iterate it several times, you start from something that is relatively weak, for example, this, and by some sort of 5-8 iterations, you get to something that is some 40% stronger than the sort of human heuristic written prover. You can, I'll skip this. You can also do this for the sort of complicated state-of-the-art theorem provers like this Enigma I was already mentioning. So here I'm showing that in some sort of 6 iterations of the learning and proving, you can get from some 15,000 proofs to something like 25,000 proofs. So in a sort of controlled scenario with 10 seconds CPU limit, it gives you something like 70% improvement by doing a lot of the machine learning on the previous proofs. So that's really unexpectedly good. Like when we got this, it really surprised us, like how far it got us. And here is one proof, for example, the cluster fixed point theorem that we can now do completely automatically. I should be wrapping up, and I think I already mentioned this symbolic guidance of sort of low-level automated theorem proofs done by Bob Verov. So this is just a teaser. You should be watching Mike Opinion and Bob Verov announcing a big breakthrough in their work with Prover 9 and hints. I will probably skip this because I'm out of time. So this is the tactical system by Thibault Gauthier doing sort of the mid-level guidance of the whole FOR system. And that has been, again, like researched quite a lot recently. I'll also skip this. What I will show you, yeah, so recently there are these systems that, for example, do program synthesis, and you can use them equally for generating programs. So here's one program generated by a transformer, by GPT-2, which actually is fake. So it's not a real proof. Like if you sort of understand the Mizar terminology, you would see that some of these steps are like totally semantically incorrect. But the interesting stuff is that the sort of transformer style machine learner can really perfectly learn the syntax and also the sort of natural deduction rules here. So the proof actually type checks. And like these sort of conjecturing systems actually can sometimes today produce new conjectures that we can automatically verify. And here is an example where it, for example, generalized a known theorem in the Mizar library from finite groups to non-finite, like arbitrary groups. And we needed to ask mathematicians, because we are stupid, whether it's true or false, because we couldn't prove it automatically, and they confirmed that this is actually provable. So it's good fun to play with these sort of linguistic technologies for generating conjectures. Okay, maybe the last funny thing to show you is this auto-formalization. So we took about 1 million examples of LaTeX and formal statements and trained neural machine translation on them, like sequence to sequence. And then we played with it. And here you can see the results. So you start training, and initially the 1000 snapshot is really bad. So it tries to translate this LaTeX into this correct statement, but it generates like a total garbage initially. But as you train over and over on these 1 million examples, the machine translator becomes better and better. And by snapshot 7000, it basically produces what is the correct statement. So that's sort of one teaser for doing the auto-formalization work, for training machine translation tools to take the huge amount of informally written mathematical textbooks and trying to turn them into this formally parsable formal languages that we can actually verify. So that's it. Here are some acknowledgements, references, and my advertisement for the Artificial Intelligence and Theorem Proving Conference, which is happening probably in a hybrid mode this year in Oslo. Thanks for your attention.
Okay, so thank you, Josef, for the comprehensive talk. So I'm just checking if there are any questions. So, well, the first one is fairly technical. On slide 6, why is there a red line in the proof? So you have this a squared is even, and why is that red? Yeah, so sorry about that. This is just an artifact of Frege-Wiedeck aligning the two statements in the informal and the formal version of the proof. Okay, so there's no actual consequence of that. Yeah. Okay. There's another question. How long will it take for a computer to win a Fields Medal?
I would say, so maybe what I can show you is a bit of these proofs that we are getting today. So what we are getting is not really something that would be beating mathematicians. So I don't know, what I got yesterday was something like this, for example. So we have like a 400 long proof in 26 seconds about an equivalent characterization of primality in a semi-lattice. So I would say, if you have never studied this, if you are some initial student of algebra, there is no way how I will give you 260 axioms and you will in 23 seconds produce a proof like this. So on one hand, like what we are now having is in some sense already fairly good, but it's not so good in doing sort of the high level stuff that the mathematicians are doing. And I would say that there is a bunch of exceptions. Like one is, for example, this work that Michael Quignon and Bob Beroff are doing on the aim conjecture, where, like I just said, like they just got a big breakthrough and they can produce proofs that have 100,000 inferences, and no human can compete. Well, maybe humans can use other methods. And actually, Michael is sort of combining the theorem theory with his sort of high-level understanding of the topic. But in some sense, I would say, if there were a Fields medal for doing quasi-group and loop theory, then Prover 9 in combination with Michael Quignon and Bob Beroff would be strong candidates these days. So in some sense, this also depends like on what the mathematical community considers to be worth of the Fields medal. I don't know that. What is sort of the interesting thing that we are definitely not reaching yet is doing this sort of more high-level planning, conjecturing, theory exploration. And I would say the sort of good thing is that if you look, for example, on AlphaGo or AlphaZero, you can also see some sort of progression there, that initially the system is sort of quite low level, but then it sort of automatically takes off just by this combination of learning and doing search and learning from the successes. And it can, in the end, become pretty good and doing some high-level patterns and very sophisticated games. So it's unclear at the moment whether something similar might not happen with our approach, like basically going from this very syntactic level where we have the sort of formal proof feedback teaching us to go to more and more high-level thinking and patterns. If you want some sort of definitive answer for me, then the standard deadline that AI researchers are putting on everything is 20 years. But I don't know, like I would probably go more like 50 years.
Okay, so I think we just ran out of time. So thank you, Josef, for the talk. Thank you for all the questions. Well, I hope to see you all in person at some point. Okay. Thanks a lot, Mikołaj. Thanks for the opportunity. Have fun with the rest of the conference. Bye. Bye-bye.